be telling you about a recent paper I put on the arXiv actually just at the very beginning of this conference. So it's a really fresh, which is about, well, this Rényi fidelities, symmetry resolution, and quantum phase transition, right? So the plan of the talk is rather simple. I will start with an introduction and tell you about these fidelities, tell you about what symmetry resolution is, and then I will exemplify this concept in the X spin chain. First, so as you know, right, studying entanglement in many body systems is a very prominent area in condensed matter and statistical mechanics. We saw many interesting talks about that in this workshop. And one thing I would like to remind you is that actually most, if not all, of the quantities we study come from quantum information science, right? So for example, entanglement entropy, Rényi entropies, mutual information, logarithmic negativity, and so on, right? So it's really the idea of taking a quantity from quantum information and applying it and computing it in the context of many body systems that actually give rise to very interesting results, right? So for example, it is related to the topology of topological phases. It's related to phase transitions, to CFT, which is also related to phase transitions, but also to out of equilibrium systems. So many interesting things come from are enlightened by these entanglement measures. But my point today is that actually you can get more from right, and Yoda agrees with me, right? You can get more from quantum information science than entanglement measures, because there is also these fidelities, which actually are not entanglement measures in the sense, in the quantum information sense, but actually still, I think, and I'm not the only one to, of course, but can also be very interesting in the context of many body systems. Right, so let's start. So the definition of a fidelity is basically from, if you have two states, rho and sigma, it tells you how similar these two states are, right? And by state, I mean density matrices with trace 1. So it can be a projector on a pure state, a Fermat state, whatever state you want. Canonical definition of a fidelity is the Ullmann-Jozsa fidelity, which reads, so you have this trace and then some function of rho and sigma to some power 1/2. And this quantity has important properties. I will just mention two of them. This first, though, it's always between 0 and 1. I mean, of course, for properly normalized states, right? And it is 1 only if rho is equal to sigma, right? So if rho is equal to sigma, you see in here, you get the trace of rho squared to the power 1/2. So the trace of rho, which is 1, right? That's the first property. And the second one is that in the case of pure states, so when rho and sigma are just projectors on pure states, psi rho and psi c, the fidelity reduces to an overlap between these two states, which is maybe the most natural way of thinking of, if you have two states and you want to compare them, you just compute the overlap. And so when you have pure states, we say that it is a pure state fidelity, and it is actually very useful to detect quantum phase transitions. So this is very old, very well known, but let me just remind you this. I think you can think of it as a distance, but it's not, it depends what you mean by distance, but I guess you could imagine it as in the Hilbert space as a distance between two states, but I am not exactly sure what the word distance.
But it should satisfy some properties to be a distance. I don't know if it does satisfy this property. Inequality.
Yeah, so I guess you could think of it. Okay, so about.
So it's a distance in the trace on the.
All right, so now imagine that you have a quantum Hamiltonian that depends on some parameter lambda with a ground state that you call get lambda, and it has a quantum phase transition at some value of lambda, which is lambda c, right? We had a very nice lecture last week about quantum phase transition, so I won't go back into these details. And now what you can do is to consider the following fidelity, right? So you consider the overlap between the ground states of lambda minus d lambda, when d lambda is a small variation of the parameter, and lambda plus d lambda. And so when you do that in the transverse field Ising model, for example, this is the type of plots that you get. So here what you have is the fidelity as a function of h. So on the left, delta H is fixed to 0.01, and you have different sizes, which are the different colors. And you see that at the transition points, there is a suppression of the fidelity, which is bigger when the system size becomes bigger. And on the right, you have here the system size is fixed, and they vary delta H, so which corresponds to my d lambda on the slide. And again, you see this clear suppression of the fidelity at the critical point. So, I mean, this was very known, etc. So today I want to introduce a measure which generalizes these quantities, which I called Rényi fidelities for the obvious reason that we have trace of rho to some powers. But of course, Rényi never works on fidelities. And as you can see, so it's again a simple function of rho and sigma, and it satisfies a natural generalization of the Ullmann-Joseph fidelity property. So it is still normalized, and it gives one when rho is equal to sigma. And for pure state, it still gives you an overlap, but just now there is some power which is irrelevant in all cases. And another thing I should mention is that when n is 1/2, the denominator here gives you 1, so it goes away. And the numerator really resembles the Ullmann-Joseph fidelity. So it is not exactly the same quantity. And in the paper, I comment a bit about that, but morally, we can say that the limit n goes to 1/2, or actually it's not the limit because nothing diverges, but for n equal 1/2, it gives you the Ullmann-Joseph fidelity. So it's really a generalization of that.
Can I just, so for n equals 1/2, rho sigma is not itself, or is it a positive operator? Because in the Ullmann, you take rho sigma rho to have something positive. It's Hermitian positive, while rho sigma is not Hermitian.
Yeah. Maybe I should have put absolute values. Or...
I mean, I don't know. You can, it's perfectly fine as a quantity. You can calculate this for n integers, perfectly fine. But if you want to take their square root and all that, like positivity, then one should maybe take something Hermitian.
Yeah, no, I haven't really thought of that. I don't exactly know, but probably.
I don't know. Maybe this is a real quantity anyway.
Yeah, I mean, sure, it gives you a number, and it was always positive in my case, but maybe one should be careful. You're right. Yeah. All right. So these are the Rényi fidelities, and what I want to do now is to compute their symmetry resolution. And so to do that, I first need to tell you what I mean by that, of course. So that's the second part. Now, so imagine now that your two states, rho and sigma, they both commute with a global charge Q. So in my case, it would be a U1 charge, but you can imagine a more general statement. So in that case, what you have is for rho and also for sigma, they both acquire a block diagonal form, right? Where each block, so here it's really a matrix, right? Here, each block is a matrix, which corresponds to the eigenvalue, a given eigenvalue of the charge. And here, the P's are the probabilities of, if you measure the charge in that state, it's the probability of observing that value of the charge. And rho of Q is the reduced density matrix for the given subsector that you are looking at. Right? So now a question you could ask is, okay, now I don't want to compare rho and sigma anymore, but I want to know in a given subsector, are the two matrices close to one another, just in one given subsector. So to do that, we can introduce symmetry-resolved fidelities as follows. So it's this cal F here. So, okay, first comment is that maybe it's not what you expected, because the trivial, the direct thing would be to just take the definition of the Rényi fidelities and just replace rho and sigma by rho of Q and sigma of Q. But actually, I want to argue that this quantity also gives you, in a sense, a symmetry resolution, because it satisfies this property, right? So the total fidelity is obtained as the sum over each subsector of this cal F of Q. So it means that if you compute cal F of Q, let me call it F of Q, then you have all the information about the given charge sector, which contributes to the total fidelity. So in that sense, it's a symmetry-resolved fidelity, but you could define it otherwise, and it's probably also interesting. But okay, it's just the first, beginning. All right, so now we know what we want to compute, but how do we compute it? To do that, we use ideas from Gaussian and Sella, which actually study symmetry-resolved entropies. And I applied their ideas to the fidelities, and what you have to do is to introduce a charge quantity. So this f of alpha here, which now has this phase in the definition. So you see that if alpha is 0, you recover the total Rényi fidelities. So that's one thing. And the second thing is that the symmetry-resolved fidelities are just the Fourier transform of this object. So this means that if you can compute this object, then you know the total fidelities and the symmetry-resolved ones, and so you know what you want to do. So now, next question: how do we compute these objects, right? And to do that, the answer, as you can probably guess, is, well, we can do it at least for free fermions, which is the usual answer, by using this connection between the correlation matrix and the density matrices for free fermions and Gaussian state. So first introduce the correlation matrices, which are the 2-point correlation matrices associated to rho and sigma, and then define these matrices. So here, J rho and J sigma, they are just trivial, convenient objects. But this J dot now is a new object, which is given as a function of J rho and J sigma. But actually, if you are familiar with the computation of fermionic negativity, this is something you have already seen, because you have to compute a similar object if you want to compute a negativity. So here it's not the same context, but it's the same type of technicalities that lead to that definition. And so once you have these, the result is that you can compute the charge fidelities as a determinants of J rho and J sigma, and then a product. Well, I mean, these are also determinant, but okay, I write them as product over eigenvalues of J dot, J rho, and J sigma. If you have a free system, you give me the correlation matrices for rho and sigma, I can give you the charge fidelities, and so the symmetry-resolved fidelities and the total fidelity. Okay, so now that we have all that, we want to see some plots, right? And see some results. So to do that, I will study the XX chain for reason that it is a simple model that you can solve. It has a quantum phase transition. And yeah, because I forgot to mention, but one of the questions was to investigate how each symmetry sector behaves close to a quantum phase transition. I mentioned that important point. So it has a quantum phase transition, and it has a global U1 charge, which it's such that the symmetry resolution makes sense. Right? There is a charge. So the chain is the following. So in diagonal form, it's that. So the important point is that the energy are these cosine and then some magnetic fields. The charge is just the fermion number, and the ground states for h smaller than 1, so in absolute value, has a fermion number, which is this number here, n over pi r cos of h. Remember that number, it will come back later. But for h bigger than 1, you see all the energies become positive. And so the ground state is actually just a vacuum state with zero excitation. And there is a quantum phase transition at this point, h equal 1. Okay, so another thing I should tell you before I move on is that in the case of pure state fidelity, so just overlaps, the symmetry resolution is trivial, right? Because the only charge sector you have is the charge, the eigenvalue of the charge on your pure state. So if you want, the density matrices are block diagonal, but with one block. So that's interesting. So we want to find contexts in which it is natural to have density matrices which are not, which have more symmetry sectors. So the first idea is to look at thermal states, right? And so thermal fidelities are fidelities between thermal states. So we introduce, recall you the definition of a thermal state, and I introduce this notation, rho plus and minus. It's just rho of beta and h plus or minus dh, where dh is a small parameter. And beta, of course, is the inverse temperature. So when you compute the total fidelities between these two objects, actually you can find an exact formula, which I don't show you here, but there is a Gaussian approximation that is here. So here, I2 is just some integral which depends on the magnetic field, and I don't give you, it's not the point to show you too many formulas today, but it is known, it's an integral. You see that n only appears through the product beta n. So in a sense, n can be interpreted as an effective inverse temperature. but this will come back also in the in the following. And you see that if DH is 0, you get 1. And this is totally normal because if DH is 0 here, so rho plus and rho minus are the same, and so the fidelity gives 1 because it's the same object. So this is the type of plot you get. So this is the fidelity as a function of h for different values of beta n. And what you see is that there is, again, a clear drop at h equal 1. And so it is not my, this was already known, this behavior, is that you can actually detect the quantum phase transition, so which is really a purely quantum zero temperature phenomena, even at non-zero temperature. So this is, this was known, but it is first good check, let's say. And I should mention that the dots are the exact formula, and the line is this very good approximation. It matches to the eye perfect. Okay, so now let's move on.
Okay, so this is an approximation. Is it valid in some asymptotic limit? Like
it is more, actually, it's just the first, yes, so it is valid in the large n limit, I should say, because this integral used to be a sum over moments, and then you integrate. And it's the first term in the DH, expansion, but it's a small parameter. So for the symmetry resolved case now, so we have this plot for Q equals 0. So again, so the dots are exact results, and the curves are some Gaussian approximation in the same type of limits. And what you get is that, again, there is a clear change of behavior close to h equal 1. Right? So here you almost have a step function which becomes sharper and sharper when the temperature becomes smaller, so when beta n becomes bigger. So yes, as I said, there is an exact and a Gaussian approximation, exact formula. And so again, it detects the quantum phase transition because there is a clear difference in the behavior close to the transition. But an important point is that actually this plot, so this was for DH equal 1 over 1,000, I think, but actually it's almost independent on DH. So this means that even if you put DH to 0, so in the case where the total fidelity is 1, this plot for the symmetry resolved fidelity will still be the same. So that means that actually at the quantum phase transition, there is a reorganization of the ground states. And the total fidelity for DH equals 0 cannot see it because the trace is still 1, but it just kind of rearranges in the matrix. But with these symmetry resolved fidelities, as you would expect, since you zoom in, you actually still see this reorganization and this phase transition. So physically it was expected, but still I think it's interesting behavior. Okay, so yes, so for Q bigger than 0 now, you have this type of plots. So you don't really see the transition anymore because you are not in the sector that is most affected by it. But what you see are this curve that becomes, sharper and sharper when the temperature becomes smaller. And actually, analytically, you can show that these peaks are located at the value of h that satisfies this integral equation. So it's an implicit formula for h. And intuitively, you would think, okay, in the zero temperature limits, what you expect is that the peaks are located at the fermion occupation number of the ground states. And actually, it's exactly what happens. So you can show that in the limit beta n goes to infinity, so in the zero temperature limit, this gives you exactly the fermion occupation number of the ground state. So the peaks are shifted because of thermal fluctuations, and eventually they go to the expected ground state value. Okay, and so before I finish, there is another context where density matrices arise naturally. It's now the case where you consider now your chain at zero temperature, but you only look at one subsystem, right? So now your whole state is in the pure state, the ground state, psi h. But now what you do is you compute fidelities between these density matrices rho A, which are traced over the complements on your system. And again, rho A plus or minus is for h plus or minus th. Okay, so this is the type of plot you get for the total fidelities. So first I should tell you that now these are just numerical results connected together. They are no longer prediction and exact calculation because of the Gaussian formula. They are actually numerically very nice, but analytically still hard to handle. That's the first disclaimer. The comments. And what you see is that still, I mean, on the left, it's f as a function of h for different values of n. And what you see again is that at the transition, there is a sharp behavior that becomes sharper and sharper for increasing values of n, which is, you know, coherent with the interpretation of n as an effective inverse temperature in, you know, in a way. And on the right, what you see is f as a function of NA, which is the size of the subsystem A. And here h is fixed very close to h equal 1. And what you see are these very big oscillations, right? With very big oscillation, which are actually reminiscent of oscillation you observe in the entanglement entropies in finite size in some systems. So I think this deserves also further investigation for sure, but it's really, you know, surprising at first glance. And a final comment maybe about that is that actually it is the first result for reduced fidelities. So fidelity between, reduced density matrices in the case where the subsystems are macroscopically big. So there are some results where you could consider the density matrix between two spins, so a 4x4 matrix. But here really, like say, like here, my subsystem size, it can be very, very big, and you can do numerics in that case. So that's a side product of this paper, but I think it's an interesting one that you can now compute reduced fidelities for arbitrarily large. All right, and so for the symmetry resolution, we get essentially the same thing as for the thermal state. That is, for q equals 0, you have this very strong, you know, behavior close to h equal 1, which is almost independent on dh. And for the symmetry resolved one with q bigger than 0, you still get this peak that get narrower and narrower and narrower, but now they are all aligned because there is no longer thermal fluctuations. So now this black line that you see here, it's exactly the ground state eigenvalue of the charge. So, again, physically expected, but I think it's a good. Okay, so with that, my talk is almost over. I will go to the conclusion. So first about what we did. So we introduced Rényi fidelities and investigated their symmetry resolution. And for free models, so free fermions, I should say, we found exact formulas for the charge fidelities in terms of the two-point correlation function. And by exact formula, I mean numerically you can compute it, but analytically it's still, as you see, a hard problem. So the total fidelity, as expected, as we knew, can detect the quantum phase transitions, and the Rényi index can be interpreted as an inverse temperature. And the symmetry resolved fidelities also detect the phase transition, but actually have a better, they are sensitive to the inner structure of the state. So even when this DH was 0, you could still see the reorganization that took place at the end. As a side results, we also gave the, at least to my knowledge, the first computation of reduced fidelities for generically arbitrarily large subsystems. So now the part that I am maybe even more excited about is actually the outlooks, because as I said at the beginning, so fidelities generated interest for sure. I mean, there have been a lot of research, but clearly not as systematic and as intense as, for example, entanglement measures. And I think that there are many, many, many things that we could do, you know, in the future. So first, we could, of course, I gave you the simplest example of the XX spin chain, but we could look at more generic quantum phase transitions and also topological quantum phase transitions. So it is known that total fidelities can detect topological order, but what about, you know, symmetry resolution in that case? It's an open problem. So the case of interacting system is, of course, interesting, but probably very hard. But inhomogeneous systems should be also amenable by these, you know, these techniques, because we know correlation matrices for inhomogeneous systems, and we could work that out. What about non-abelian symmetry? So when the symmetry is not just U1, but a more, you know, complicated one. Again, open question. Computation in CFT, like it's trace of density operators. Again, I think we could compute them. And then there are many things that are actually already in progress. So for example, these fidelities can be used as probe of symmetry breaking. So this is something that we are already working on. You can also study the dynamics after quantum quench. So this is actually a baby of this conference, because I was discussing this with Vincenzo Alba last week, and we already have some quasi-particle picture, and so many things to do there. We can also generalize this formula for free bosons, because I just show you the case of fermions, but again, that's in progress. And I think that maybe the key point is that many, if not all, questions that you can ask about entanglement measures can probably be investigated through the lens of fidelities. But the only thing is to know what to ask. So which state to compare and what physics can you get out of it. But I think there are many things that we can do in the future. And with that, I thank you for your fidelity.
Thank you very much for this nice talks. Are there any questions?
So the fact that this is one after, this is completely trivial, because I mean, because the ground state is the vacuum state for h bigger than 1, so the charge is 0, and that's the only charge there is, right? So that's completely expected. But the very strong drop at 1, I mean, when you look at the other fidelities on the right, even when you go after their expected value, which is their ground state value, they don't fall that fast, right? So, but the fact that it's 1 for q equals 0 after for h bigger than 1, that's completely. This is the only thing I was sure of when I started this. At least that's the sign of the transition.
Are there maybe quick questions? All right. Yeah. Thank you very much. Let's thank Gilles again.